Hi everybody, this is Dr. Pingle here with the applied portion of the map design research lecture. So what I have here is a layer loaded into ARC. So this is data that came from the county health rankings, just joined to some boundary layers from the census. So what we're looking at here is the percent of children in poverty by county in the lower 48. So you can sort of see the overall pattern here, patterns in the south, in eastern Kentucky, West Texas, Arizona, New Mexico, and so on. So where does this classification come from? So we can see the breakdown over here on the left. And this is just the default symbolization. So if we had opened the layer, this is what it would look like. The classification, you'll notice, says natural breaks and Jenks. So this is the same George Jenks that we were talking about in lecture. So natural breaks is an algorithm that's going to try to look at the distribution of data and make these classification breaks according to its own optimization routine. And what that optimization tries to do is it tries to minimize the difference within a category. So these are the different break values. This is a histogram of the data, and in blue you can see the breakpoints, the same ones that we see over here. And so what the algorithm is trying to do is it's trying to minimize the variance within a category. So within this, we want to try to minimize that as much as possible. And we want to try to maximize the difference between categories. If we had any big discontinuities in our data, we would be using those to break down this data set. Since this is more or less normally distributed with kind of a long right tail, the algorithm is kind of working differently. So you can see sort of we've got from the minimum value up to sort of a low threshold. We kind of have a middle value, a high value, a very high value, and then kind of an extremely high value. So the algorithm's job, the natural breaks algorithm's job is to sort of bring out or highlight these differences. And that's why it's the default classification method for ARC. It's obviously not the only method. There are plenty of other methods in here. And you should definitely be investigating those whenever you're making a choropleth map. But it's not a bad first cut. One of the things that's required for the algorithm is the number of classes. So as you increase the number of classes, it's going to be looking to optimize those classes in the same way. So classes is sort of a default. So we'll hit OK. I wanted to show you another area where there's a component of map design research, and of course map design research has impacted many of the things that you see within ARC, so I'm really just highlighting a couple of these. So I'll turn on a populated places layer. This was downloaded from Natural Earth. These are populated places kind of within the view screen here that have a population larger than 1 million. And I'm going to zoom in to this point over here. So what we've got is a what's called a proportional circles representation here. These are point data associated with the city, and what you're looking at here is the size of the circle. I'll open this up. The size of the circle is scaled to the size of the population. So what I wanted to show you here is a checkbox that's right here. So I'll hit apply here. This checkbox says appearance compensation, and then in parentheses Flannery. So Flannery is again another name that kind of pops up a lot in GIS. This was a student of Arthur Robinson's that did some research on the perception of map symbols. There's a really good article about this online in Making Maps and DIY Cartography. And I would encourage you to check this article out. It's an old post, but a good one. All about the perceptual scaling of map symbols. And the idea here is that people are very bad or they have biases anyway at estimating the relative sizes of circles. And so if you go to ask people, how much bigger is this circle than that circle, they'll often underestimate the area. So if you have one circle that's twice as big as the other, they might estimate it at 1.5 times, for instance. And the actual amount that they would misestimate or underestimate depends on the sizes of the circles themselves. And that's kind of what this graph is getting at. And so the idea here is that what you want to do is you're basically going to give a little bit of a boost to the larger map symbols so that people make those judgments more accurately. So Even though this circle is not 12 times bigger than this circle, these are the essentially the true areas. What we want to try to do is bump those up a little bit so that people can more accurately make those estimations. So if you measure these out, they're not correct, but if you ask people what the right answer is, they would be more correct as a result of this Flannery compensation. So when we check this box, you'll notice that the maximum value size gets larger. Here we've got the populations of San Jose and San Francisco. San Francisco is about twice the size of San Jose. And by checking that box and hitting apply, you'll see the size of this circle proportional to this one just get a little bit bigger. They'll all get a little bit bigger because they're all related to a minimum value here. But ultimately, this should help your map readers make more accurate judgments. So those are just two simple examples of where map design research has greatly impacted ArcGIS. So the George Jenks natural breaks and the Flannery compensation for point symbols. There are many others, but those are two good ones. So thanks for listening. We'll catch you next time.